Assalamu alaikum students. Welcome to the chemistry lecture. I am your teacher Sumayya Khan. We are doing chemical thermodynamics and we have completed most of the part of the chapter. Okay. Today inshallah we will finish the chapter. So let's begin with today's topic. Today's first topic which we'll discuss today is you can see here it's Hess's law of constant heat of summation. Hess law is very simple law. It states that the enthalpy change for a reaction remains same whether the reaction takes place in one step or in a series of steps. Okay, we know that enthalpy is a state function and it depends only on the initial and final state. Okay, so it means that what path is taken to reach that final state will not have any effect on the total enthalpy change for a reaction. Okay, so it can be stated in many different ways. I have here displayed two definition of Hess's law, which states that the first one says the enthalpy change for a reaction is same regardless of the path followed to reach that state. Okay, and the second one says that overall the enthalpy change for a reaction is equal to the sum of the enthalpy changes of individual steps in the reaction. So all these statements are saying the same thing. It says that regardless of the path or regardless of the number of steps involved in the reaction, the total enthalpy change for the reaction will remain same, because enthalpy is a state function and it depends only on the initial and final state. Let's take one very simple example. Suppose there is a reaction where we are seeing that A is converting to B. Okay, now this conversion of A to B can occur in a single step, or it may occur in several steps where A will first convert to C, then C converts to D, and then D converts to B. Okay, so this conversion is possible in two different ways. Okay, one is where the A is converting directly to B, and the other way is where A is first converting to C and D and then reaching to B. Okay, so here you will find that the delta H of this reaction is same. Okay, so delta H is equal to sum of the delta H1, delta H2 and delta H3. Okay, so this is what Hess's law cycle to explain what is mean by Hess law. Let's take one actual example again. Now consider the synthesis of ammonia, where 1 mole of nitrogen is reacting with 2 moles of hydrogen and forming N2H4 gas. Okay, this is not ammonia. Now this N2H4 gas, for this first step, the enthalpy of reaction is found to be 95.4 kilojoules. Okay, then in the next step this N2H4 reacts with another 1 mole of hydrogen and forms 2 moles of ammonia. For this reaction the enthalpy change is found to be minus 187.6 kilojoules. Okay, so what we have seen here, we are seeing that the enthalpy change for the first reaction and the second reaction is this and this. Okay, so what will be the total enthalpy change for the overall reaction? So now we are writing the overall reaction. We can see here that N2H4 is formed as well as used in the reaction, therefore N2H4 gets cancelled because it was a intermediate. Now what are we left with? We are left with 3 moles of hydrogen and 1 mole of nitrogen on left hand side and 2 moles of ammonia on the right hand side. Okay, so when you add the two equation, you will get your overall equation and your enthalpy change will comes as minus 92.2 kilojoules, because minus 187 plus 95.4 will give you 92.2 kilojoules. So whether this reaction is taking place in the single step or it is taking place in two steps, the total enthalpy change will remain 92.2 kilojoules. Okay, so this is very simple way of understanding the enthalpy of Hess's law of constant heat of summation. What is the use of this Hess law? Hess law is very useful in finding out the enthalpy of such reactions whose enthalpies cannot be calculated directly or experimentally. Okay, so what is the application? The Hess law has been useful to calculate the enthalpy changes for the reaction with their enthalpies being not known experimentally. So there are many reactions whose enthalpies we don't know. For example, in our previous lectures we had a conversation regarding the standard enthalpy of formation. I have told you that we don't, the standard enthalpy of formation reaction, the reaction which we write for formation do not occur naturally. So where do we get these values from? We have the value of standard formation for many different compounds. So where are we getting these values from? These values can be calculated with the help of Hess's law. How it is calculated, that we will discuss when we will see the problem based on the Hess's law. Remember, in thermochemistry, the chemical equation can be treated as a mathematical equation where they can be reversed, multiplied, or added or subtracted. Okay, so this was all about the Hess's law of constant heat of summation. Now, what is entropy? Entropy is another important thermodynamic property which helps us in determining the spontaneity of a chemical reaction. Now look, we are not going to discuss in detail about the meaning of spontaneous process, but it is very simple to understand that spontaneity or spontaneous processes are those processes or reactions which occurs on its own without any external effect. Okay, so there are many things, or there are many natural processes which we observe in our day-to-day life and which are spontaneous. For example, the flow of water from high level to low level, the mixing of the two gases when they are allowed to mix, the mixing of sugar into water or salt into water, all these are what natural processes. Okay, it does not require what external influence for taking place. So these processes are known as spontaneous processes. Okay, now entropy is helpful in finding out whether the given reaction would be spontaneous or not. So let us first understand what is the meaning of entropy. Entropy is defined as the degree of randomness or disorder in a system. It is a measurement of the degree of randomness or disorder in the system. If the system is having less order, it means it is having more disorder and more entropy. If the system is having more order, it means it is having less disorder and less entropy. So it is related to the disorder or randomness which is present in the system. Higher disorder means higher entropy, lower disorder means lower entropy. And this can be also associated with the amount of energy present in the system. If the system contains more energy, it will be having more energy to perform motion, and it will observe more disorder or randomness in the system, causing greater entropy. In the same way, if the system possesses less amount of energy, the molecules or the particles of the system will have less energy and they will move less, and therefore there will be less randomness or disorder and lesser entropy. Okay, so the lower the entropy, more it is ordered and less random it is, and vice versa. Okay, here one diagram flow chart is given where you can see there are square boxes in which some particles are shown with the red dots. Okay, so in the first, the particles are randomly dispersed. It means it has very high disorder and high entropy. As these particles they come closer to each other, their randomness will decrease, and in the last one all the particles have combined into one entity, and that will have the least randomness. Okay, for example, when you are in the classroom, when the teacher is present, all the students are on their place, okay, sitting properly. So there is less disorder in the class and there is less entropy. When your bell goes off, when the teacher moves out, everybody start moving around here and there. So all of you get scattered, and you will observe what? Randomness or disorder in the classroom. Okay, so there will be more entropy. Understood? So you can try to remember the meaning of entropy in this way. Okay, it is the measurement of degree of randomness or disorder in the system. Okay, now here I have shown one example where you can see the example of ice, water and its vapor is taken. Okay, in ice we know that ice is solid. So in ice, the molecules, water molecules are nicely packed together, have their fixed position. Okay, so it has order in its structure, therefore it will have least entropy. When this ice melts, the water molecules, they are still intact with each other, but the structure, the order which was there in the solid is broken down, it collapsed, and now you have a disordered state which is a liquid state. In the same way, when the liquid evaporates and gets converted to gas form, all the molecules of water are now free to move here and there. They will have the random motion and you will have the highly disordered state. Okay, so when you go from solid to liquid and from liquid to gas, you are going to observe the increase in disorder, therefore increase in entropy. Now the conversion of ice to liquid and to vapor is what? A spontaneous process. We know that if you will keep an ice on normal temperature and pressure, it is going to get converted into the liquid, and that liquid, if left, will get converted to vapor after some time. Okay, so this is a spontaneous process. Okay, and where we can observe the change in order of the system. Okay, but sometimes it is very difficult to find out what is happening to the order of the system when we are observing any chemical reaction. It is not necessary that all the time the disorder can be observed due to the changes in the physical state of the system. It is possible that the system is still in the same solid or the liquid or the gaseous phase, but still the entropy of the system is changing. To find it out, what we can do? We can take the help of the formula which says that the change in entropy delta S is equal to the Q reversible upon T. This is what? A quantitative definition or expression for the entropy. What is Q reversible here? Q reversible is the amount of heat that is transferred to the system in the reversible manner. Or you can easily think of a system in which the system is present at certain temperature. If you provide more heat to the system, what will happen? And what if you remove some heat from the system, what will happen? Now let's take the first case first, which says that if we add heat to the system, if you add heat to the system, what happens? The particles which are present in the system will get some extra amount of energy. Because of that extra amount of energy, these particles which have their particular kinetic energy, their kinetic energy will increase and their movement will also increase. Okay, when there will be more movement, where there will be more disorder. Okay, so when the heat is added, the energy of the system rises and the disorder of the system also increases. In the same way, if the heat is removed from the system, the energy which was present in the system is being removed, so the system's energy will get lower. The particles will now have the less energy and they will do less motion. Thus, there will be less disorder and the entropy of the system will decrease. This is why the change in entropy is directly proportional to the Q reversible. If heat is given or increased, the entropy will increase, and if heat is removed or it is given out, the entropy of the system will decrease. Understood? So delta S is equal to Q reversible upon T is what? Your quantitative expression for entropy. Now what is the unit of it? Its unit is joules per Kelvin. Okay. Now you may be asked to justify the presence of Q and T for defining the delta S. Now I have told you earlier also, heat is delta S is directly proportional to Q reversible because the heat is responsible for the kinetic energy of the particles, which are atoms, ions, or whatever they are, molecules present in the system. So if they will get more energy, they will do more motion and there will be more disorder, and if they will get less energy, there will be less motion and there will be less randomness or disorder. Okay, now what is how the temperature affects, why it is inversely proportional to temperature. Look, temperature of the system is what you can say is we can say that it is responsible for the entropy that is already present in the system. Suppose there is a system which is already at a very high temperature. If the temperature is high, it means there is huge amount of heat already present in the system. So this temperature is accountable for the amount of entropy that is already there in the system. Okay, now if a temperature is already very high and you are adding small amount of heat to that system, you are not going to observe what a significant increase in entropy. But if the temperature was low and you are adding the same amount of heat at that low temperature, you are going to observe a significant change in the entropy. For example, suppose you have one huge pile of chocolates and another pile of chocolate in which you can say there is only 10 chocolate and there is 100 of chocolate. You have two piles, one pile is of 10 chocolates and one pile is of 100 chocolates. Okay, now if someone removes 2 chocolate from the pile of 101 and from the pile of 2, you are going to notice the decrease in amount which is there in the pile of 10. You will not be able to catch that someone has taken 2 chocolates from the pile of 100 chocolates, but you will definitely going to catch that someone has taken 2 chocolates from the pile of 10 chocolates. In the same way, if in it someone is adding 5 chocolates into the pile of 100 chocolate and 10 chocolate, you are quickly going to observe that your pile of 10 chocolate has increased in number, has gone to 15, because when the disorder is already less, it is easy to observe, or the small changes will be recognizable. Okay, you will be easily able to recognize the changes. But if the disorder is already high, the small increase or decrease in temperature, that is addition or removal of heat, will not be that significant. In our previous book, very good example was given. Suppose you are sneezing very loudly and you are sneezing at two different places. Suppose you are sneezing into a quiet library and at a railway station. If you will sneeze at the railway station, nobody will notice because railway stations are already very loud. Okay, but if you sneeze in a quiet library, everybody will notice that you have sneezed. Okay, so you are sneezing with the same intensity, but this sneeze is significant only when there is less noise. So remember students, the temperature of the system is accountable for the disorder that is already present in the system. If the temperature is already high, the small addition or removal of heat from the system will not be very significant. But if the temperature is low, it means the entropy is less. The small increase or decrease in heat or addition or removal of heat will be very significant and observable. Okay, and this is how we define or justify the presence of Q reversible and temperature into the definition of delta S. Okay, so here we have finished. Okay, that's it students. Our chapter is over here. We have finished the chapter. Only numericals are remaining. We'll do the numericals when the normal class will begins, okay? So all the theoretical part is finished. I hope you all are studying. If you have any difficulty, please mark those difficulties and we'll discuss those in the classroom, okay? Allah Hafiz.